Hi everyone. So one of the things that happens in math is that the classes have these fancy sounding names like linear algebra, complex analysis, and you might not even know what you're getting into. So I want to start just by answering the question of what is linear algebra? And before I erase it, I want you to enjoy this nice picture that my 5-year-old son drew. So the question, what is linear algebra, is actually a little bit complicated because it's an old subject that has evolved over time. Originally, linear algebra is about solving systems of linear equations. So here's a simple example. 2x minus y is equal to 8, and x plus y is equal to 7. So when you're solving this, you're trying to find values of x and y that satisfy both equations at the same time. Now, you've probably seen systems like this before, so I'm going to ask you to hit pause on the video and try to solve it yourself before going on. Okay, did you solve it? So the answer is x equals 5 and y equals 2. And you can check this just by plugging the numbers in and seeing that it works. So if you plug in x equals 5 and y equals 2, you get 2x minus y is 10 minus 2 is equal to 8. So it works. And then if you plug it into the second equation, you get 5 plus 2 is equal to 7, which is true, so it works. So we know that this is actually a solution. But let's talk about how you would have obtained this solution. There are basically two different techniques that you might have used. So one technique is that you could have tried to eliminate a variable. So here's how that would work. So you start with the original system of equations, and then you observe that if you were to add these two equations together, the plus y and the minus y would cancel out. And then you're just left with the equation 3x equals 15, so x is equal to 5. And then you could plug that back into one of the other equations to solve for y, and you'd get y is equal to 2. I'll point out that the way I did it, I eliminated the variable y, but you could have also done it in a way where you eliminate the variable x. For example, you could multiply both sides of the second equation by 2, and then you'd have a 2x in the first equation and a 2x in the second equation, and you could subtract one of those equations from the other one, and then you'd eliminate x, and you'd just have an equation for y, and you'd solve for y equals 2, substitute back in, and get x equals 5. So the second technique you might have used is substitution, and here's how that would work. You would take one of the two equations and you would solve for one of the variables in terms of the other variable. So for example, I could take the second equation, and if I solved that second equation for y, then I would get y is equal to 7 minus x. And then I could substitute that into the first equation. So then I'd have 2x minus parentheses 7 minus x is equal to 8, and I could expand the parentheses, simplify, and solve for x. So if I simplify the left side, then I get 3x minus 7, and then when you solve 3x minus 7 equals 8 for x, you get x is equal to 5. And then again, if you plug that back into the equation that we just had for y equals 7 minus x, you get y is equal to 2. Okay, so the system of equations we were just looking at has two variables, but in general, in linear algebra, we're going to learn how to solve systems of equations that have 3, 4, 5, maybe even 1,000, maybe even 1,000,000 variables. So to avoid giving a specific number to the number of variables, we just say n variables. Now, if you have two variables, you might call them x and y. If you have three variables, you might call them x, y, and z. Eventually, you run out of letters. So the common way to handle this is to use what are called indices. So that just means we use a numerical subscript to label the different variables, x1, x2, x3, x4, and so on. So for example, a system of 4 variables might look something like this. So here I have a system of 3 equations in 4 variables. So one thing to keep in mind is that the number of equations and the number of variables don't have to be the same. There could be more variables than equations, there could be more equations than variables, there could be the same number. And another thing that's worth pointing out is that this last equation doesn't have all the variables, and that can happen. You could have equations that don't have all the variables. You could have an entire system of equations where one variable just isn't there. but you still know that that variable is part of the system. And so it's important that, the way that I've written it sort of lines up the x1 variables and the x3 variables together so that you can sort of see where there's missing variables. And you could interpret those as just being zeros. And later on, we're going to work in a context where we would actually fill in those zeros explicitly. And then the other thing to keep in mind, and this is why this is called linear algebra, is that these systems are of a particular type that are called linear systems. And what that means is that the equations are just built out of very simple pieces where you just have a constant times a variable, plus constant times another variable, minus constant times another variable, and so on. You don't have quantities like x1 squared or x1 times x2 or like sine of x1 or e to the power of x1. It's just constant times x1, constant times x2, constant times x3, constant times x4, and then equals a constant. So those are called linear equations, and when you have a system of such equations, it's a linear system. So at this point, I'd like you to pause for a second and don't do any work, but just think about how you would go about solving this system. It's a lot harder, isn't it? You might have thought, like, okay, I can eliminate one of the variables, but then you still got all these other variables there. Or you could solve for a variable and substitute, but then that's actually a pretty long computation, and it would end up taking a lot of work. So the first thing we're going to do in this class is we're going to learn a method for solving linear systems of equations. And it's going to be a general method that always works, no matter how many variables there are, no matter how many equations there are. So it's a pretty powerful thing. And something that also we're going to keep in mind is that in practice, it's still not something that you're going to want to do by hand if you have like an equation involving 20 variables. But it's a method that you could program into a computer, and a computer could actually do very quickly, even when there are hundreds, thousands, millions of variables. So now I want to go back to the system that we talked about at the beginning, 2x minus y is equal to 8, x plus y is equal to 7. There's a nice geometric interpretation here. And that's that I could interpret each of these equations as being the equation for a line in the xy plane. It might help to solve both equations for y, so you can write it in the form y equals mx plus b, and then you can graph those lines using the slope and the intercept. So y equals 2x minus 8 has a y-intercept of minus 8 and a slope of 2, and y equals minus x plus 7 has a y-intercept of 7 and a slope of minus 1. And so you can see that these two lines intersect each other. And I didn't really make an effort to draw it to scale, but you can even see here that it looks like the solution we found is reasonable from the geometric perspective. So the solution we found, x equals 5, y equals 2, is actually the intersection point of those two lines. Now this geometric interpretation has analogs in higher dimensions, but it becomes increasingly difficult to visualize. In 3 variables, a linear equation is the equation of a plane. And so if you have a system of equations in 3 variables, each equation represents a plane, and then you're trying to find intersection points between the different planes. And you could imagine, it's hard to draw pictures, I'm not even going to try right here, but you can imagine 3 planes intersecting so that the common intersection point is a single point. And actually, like in your head, you can imagine like the corner of a room where you have one wall is one plane, another wall is another plane, and say the floor is another plane, and then they all intersect at that corner. So that's a single intersection point. And in more than 3 variables, it's basically impossible to visualize, but you can sort of use the idea of lines and planes as analogies, like pictures that you have in your head, even when you're thinking about 4, 5, 6 dimensions. And the term for this is hyperplane. So if you have an equation, a linear equation in n variables, then that represents a hyperplane in n-dimensional space. So then when you have a linear system in n variables, then you're trying to find points where all those hyperplanes intersect. Again, it's basically impossible to visualize, but you can think about intersecting lines in the plane, intersecting planes in three-dimensional space. There's some higher dimensional version of that picture. So this leads us to some good questions that you could ask about linear systems. So if I give you a linear system, does a solution even exist? Not necessarily. There actually do exist simple examples of linear systems where solutions don't exist, and I'll draw a picture for you. Parallel lines, they don't intersect, and so if you have one equation that represents one line and another equation that represents a parallel line, then that system won't have any solutions. Next question, if a solution exists, is it unique? So in the example we did at the beginning of the lecture, there was a unique solution, x equals 2, y equals 5. But you could imagine linear systems where the solution is not unique. In fact, a single equation is a perfectly good system. You could have a system with just one equation, and then that solution would be an entire line. So like every point on that line would be a solution. That means it's not unique. There's an infinite number of points on that line. So then if it's not unique, what does the set of solutions look like? And so we're going to spend a lot of time describing what the set of solutions look like from different perspectives. Now, everything that I've said so far is pretty classical math, going back hundreds, if not thousands of years. But this is really just a third of the course. And after this point, we're going to make a leap into what's really a more modern perspective, where we extract the key features that make linear systems work and that make it possible for us to solve them easily. And then we recognize that these features actually exist in a lot of different other contexts. And it would be impossible for me to describe in a couple of seconds all the different contexts where it would appear, but let me just give you one simple example, and that's the derivative. You would have learned in your calculus class that the derivative satisfies some simple properties with respect to addition and multiplication by constants. Basically, that if you take the derivative of a sum of two functions, it's just the derivative of each function added together. And if you take the derivative of a constant times a function, you can pull that constant out. Because the derivative satisfies these properties, there's a sense in which equations involving the derivative behave in a similar way to linear systems of equations. And we're going to make that relationship more precise later in the semester. But just to give you an idea, think about an equation like this. The derivative of f of x is equal to 2x. So if I wanted to solve an equation like this, then I'm trying to find the functions f of x, which when I take their derivative, I get 2x. So this is something that you would have actually studied in calculus, and you can solve it just by taking the antiderivative. And so the solution is that f of x is equal to x squared plus c. Okay, now think back to the previous slide when I told you that if you have a single equation in two variables, then the set of all solutions is an infinite set that form all the points on a line. In this particular case, the set of all solutions is an infinite set because this c can take any value. But there's a sense in which you could say that this set of solutions falls on a line inside some infinite dimensional space of all functions. It's a little bit crazy, but we're actually going to make this idea more precise later on. And it turns out to be really, really useful for studying differential equations of this sort. So that was a good segue into talking about applications of linear algebra. And there really are so many applications of linear algebra, it would be impossible for me to mention them all. It really is like linear algebra is everywhere. But let me just give you a few big ones. So as we just saw, differential equations are an important application. And they actually come up in a lot of different situations. So linear algebra can be used in different ways to study differential equations. So there's linear differential equations, which is the one that we just saw as an example of that. So it's a particular type of differential equation where the solutions can be interpreted as falling on a line or on a plane or something like that. There are systems of differential equations. So this is where you have different quantities that are interacting with each other. And these types of systems, really, any real world problem is probably modeled by a system of differential equations. Whether you're talking about like supply and demand in terms of economics, or a model for studying the spread of a virus, where you have people that are infected and people that are susceptible, um, or predator prey systems, or even studying hormonal systems inside of the body. They can all be modeled by systems of differential equations, and linear algebra comes up in those contexts. There's Fourier analysis, which roughly speaking has to do with like taking a function and breaking it up into sine waves, sine and cosine waves, which could be interpreted in terms of music, where you have like the sound wave of music being broken up into its individual frequencies. But there's a sense in which everything is a wave: light, heat, sound. Even in quantum mechanics, they would say that even particles themselves are just waves. So Fourier analysis ends up popping up in all kinds of places anytime you're studying things at a sufficiently complex level. So as I just alluded, quantum mechanics is another important application. We probably won't get a chance to talk about this in any detail, but I'll try toward the end of the semester to say a little bit more about this. But there's a sense in which quantum mechanics is linear algebra. It's almost like the two subjects are just different ways of looking at the same thing. So it is actually a really important application. And it feeds back in both directions. That linear algebra helps to study quantum mechanics, but quantum mechanics also helps to give some intuition and understanding to what's going on in linear algebra. So linear algebra comes up in geometry. One way, this is another thing where it comes up in a lot of different ways, but one way is that it gives you some language for studying symmetries. So like if you have something like a cube and you want to talk about the different ways that you can rotate the cube so that it looks the same after you rotate it, you can describe those rotations by linear systems. And so those linear systems can describe these symmetries. And this study of symmetries has real-world applications. One is to computer graphics, because that actually involves manipulating three-dimensional things. And another one is to chemistry, because you can actually study the structure of molecules by looking at the symmetries that they have. Another application is statistics, and we'll talk about this a little bit in the class. The idea is that if you have, let's say a best fit problem where you have some data and you're trying to find a line that fits the data, the problem of finding this line can actually be expressed in terms of a linear system of equations. And the idea is that, well, you can't exactly solve that system of linear equations because you can't find a line that passes through all of the data points, but you can find the best approximation to that solution. And we will actually talk about that later in the semester. And then finally, a really important real-world application is to what people are calling big data, which is basically when you have very large data sets and you're trying to make sense out of them. Linear algebra provides you with some tools that you can use to study that data. So for example, the algorithm that Google uses to give you its search results, or that Netflix uses to decide what movie you're going to want to watch that night, those actually use linear algebra. Okay, that is the introduction to the course. Please let me know if you have any questions.